Assalamualaikum warahmatullahi wabarakatuh and good evening. Today we are going to make a presentation video about the subject of BERN 2413 digital system, and these are the members that will be making the presentation. Firstly, it's ALIF NABIL bin ADNAN and me myself Muhammad NASRULLAH bin ZAKARIA, and next is Leslie Tan, and finally Daniel ISMAIL. Okay, next. Okay, for our project, it will be project question number 5, which is an implement a binary coded decimal or BCD counter using Verilog. The counter should increment every clock cycle and display the count value in BCD format using the force 7-segment display module. We will also making a design a test bench to verify the functionality of the module. So maksudnya kita punya projek soalan kali ni untuk kami adalah untuk menggunakan BCD dan juga 7 segment display untuk keluarkan nilai yang kita orang nak, dan kita orang perlu buat test bench dan juga coding untuk verify lah dia punya function dia. And next. Okay, what is a 7-segment display functionality? It is a 7-segment display, and it has a numeric indicator which has 7 LED segments. Each segment will have either an anode or cathode, allowing the representation of the decimal number that will be the input. So contohnya kita ada 7 LED ni, dia akan hidup untuk menunjukkan nilai yang kita nak lah. Next. Okay, next is binary code decimal, BCD. It is a binary representation of decimal numbers, which each digit is represented by a 4-bit binary code. Contohnya kalau kita orang letak 000 dan nilai tu akan masuk di input A, B, C dan D. Dan kemudian dia akan jadi output dia kepada A, B, C, D, E, F dan G. Nilai-nilai itu akan menunjukkanlah kalau contoh 000, dia punya decimal dia akan dapat nilai 0 lah. Okay, next.
Thank you, Nasrullah. I will continue the presentation. This is the state diagram. The truth table is a tabular representation that show all possible combination of input value for logical function or circuit and the resulting output. Seperti yang anda nampak, jika ini adalah jika circuit mendapat positive edge clock signal, dia akan jadi 001 dan seterusnya sehingga 1001, iaitu 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 ni dia akan ditunjuk pada display. Next. Next is BCD truth table. The BCD binary code decimal truth table should associate each decimal digit 0 to 9 with its corresponding 4-bit binary code, facilitating the representation of decimal number in binary form. Seperti yang anda nampak, binary input 0000 adalah starting dan akan mendapat G-nya untuk decoder output akan jadi 0. Jadi pada 7 segment display output akan menunjukkan nilai 0 dan seterusnya. Untuk binary input 0001, decoder output B dan C akan mendapat nilai 1, dan pada 7 segment display output akan menunjukkan 1 dan seterusnya sehingga 9. Okay, seterusnya. Ini ialah, this is the block diagram for 7 BCD 7 signal. Untuk inputnya ialah clock dan reset dan outputnya ialah BCD out 3 nisbah kosong. Seterusnya. Next.
Hi, this is Daniel. So I'm going to explain on the coding side of the Verilog. So here we make a module named BCD counter. So inside the counter we have the input and output mentioned. So we have the input wire named CLK, which stands for clock, and we have the input wire named RST, which we know as a reset, and we have an output register which has a 4-bit data address within its array, and we have named it as BCD out. So in the register, and then we have the register 4-bit, and we named it as count. So in this code where the code began, then it's began from the count as binary, and I'll be explaining the code from the next page onwards. Okay, so this is what I already mentioned about our initialization. So the module input, inside the module we have the input and the output and the register named count, which is 4-bit data, and then there we have. So in this, from here the loop it starts working. So this is a unstoppable loop, or we know as while loop. So in this loop, first if checks the if else statement checks whether the reset value is true or false. So if the reset value is true, then it's going to begin this executing the lines. And if the reset value is false, or if it's a 0, then it's going to begin this. And then we have another if else statement, but I'm going to talk about the first statement, if the if else and the else. First if else. So let's say it's a true. So when the reset is a true, so the reset it gives an output of 1, which is high. So when it's high, the count, the variable count, it became binary 0. So in decimal it's 0. And the BCD output is also 0. So that means in the 7-segment display, let's say when the input is 0, and the 7-segment display is going to be 0 as well. There will be no LED will be turned on. Okay. So and then it's going to execute the whole code, and it's going to come back at, and when it does that, the count will be when it goes through this line, the count should be, this time it would be it will be here. So when it execute the whole code and it will be here again, then the reset would be false this time because we haven't triggered the reset yet. So now rather than going into this, because the reset is false, the reset is not triggered, it will go into this line, which is the count. So the count is going to be and then here we have another if else statement. So if the if is 9, which is decimal 9, and then it will make it 0. And if it's not 9, then it will count another, it will make +1 with the count. So at the first time, it was 0. So when it was 0, the count became, the count came into this code again, and then the reset was false. So the code jumps here, and the count is not 9 because it was 0. So rather than going into this if statement, it's going to go to the else statement, and the count this time it would be count +1. So 0 + 1 is going to be 1, and then it executes the whole code, and it come here. The reset is going to be false. It's going to go to the in the else statement, the second in the if else statement inside the else. This time it's also not D9. It's not 9 yet. It's what it is. We know it's 1, and then it's going to go here again due to its condition, which is it's not 9, and then it will be 1 plus 1, which is going to be 2. And it will be doing it until it became 9. So when it becomes 9, and then the count would be forced to become 0 again. So this is the whole method of how we are counting, how we are playing the logic of the count variable. Okay, and then we have a case count. So remember, we are talking about how the count works. So this time when the count works, so we know it's going from 0 to 1, 2, 3, 4. If it's not, if the reset is not high, if the reset is high, then it's going to start from the very beginning. But when the reset is not high, it's going to count from 0 to 9 according to our preset of algorithm. So here we made a switch statement machine, a state machine where if the decimal, if the count is 0, then the BCD output is going to be 0, 0, 0, 0 as well. If the D1, which is if the count is 1, then this is going to be our BCD output, and it goes on until it becomes 9. So when it becomes 9, and then the count it became 0, and it goes to the default function. So yeah, and then it ends, it's executing, and then it goes to the initial stage. So now my friend Leslie, he'll be explaining the test bench onwards. Thank you.
Thank you, Daniel, for the explanation about Verilog coding. And for the test bench coding, we will have our VCD counter. So for line 2, we declare our module as VCD counter. And inside VCD counter, we have our input wire circuit, which is clock. Another input wire is reset, and upper wire is VCD count. And then for 7 display, we have our module, which is 7 underscore sec underscore display. Inside it, we have input wire, which is 330 BCD, and the output register is 60 segments. And for the test bench module, we have TB underscore BCD underscore display for the test bench module. And the clock and reset signal, we have clock and reset. And this is our simulation and result. So thank you for your valuable time. That's all for our presentation. Thank you.